Hey 13 diplomas, and welcome back to topic 17. This is the final lesson for this part. This is part D. So here you'll see where we started this last time. This is calculating the Kc at 300 Kelvin for the oxidation of iron. So here's the oxidation of iron. This is one of the reactions as part of rust. So instead of giving you G this time, they've given you an enthalpy and they've given you an entropy, and you have to calculate G to plug it in to solve for the Kc, the ln K. So just be mindful, they might often do this to you, give these in different units. Make sure you just convert one of them to kilojoules. So this one, it's the S that needs to be converted to kilojoules by dividing by 1,000. So then you can just plug into your G equation, which we've used before, and you get a large negative G. We know a large negative G means the reaction is spontaneous and the equilibrium favours the products. So now we can kind of link that in and confirm it with the Kc by calculating the Kc. So we rearrange this equation given in section 1 of your data booklet. Just be mindful that G must be in the same units as R. So we need to have joules per mole, not kilojoules. So that's why this has been times by a power of 3. So once you do that, you get 298. So that's ln Kc. So to get Kc, we need to do e to the power of 298, and that gives you this enormous number of 2.6 times 10 to the 129. That's a huge value, massive, massive, massive. So basically what they're saying is, or what that number shows, is that products are being favoured, and so much so that basically the reverse reaction doesn't even happen. So that's really cool. That confirms a couple of things. We've got a large negative G, which we know means spontaneous. We've got a large Kc, which we know favours the product. So this is all linking in nicely. But the problem here is it doesn't tell us anything about rate. Like this reaction, yep, it's spontaneous, okay, cool as, but actually it happens so super slowly, and this tells us nothing about that. Just really quickly before we move on, different reactions have different values of Kc, and that's because they all have different values of G. And why do they have different values of G? Because they've got different enthalpies and different entropies, which is pretty cool. So the final thing is that we can actually link in your equilibrium constant to rate constants and kind of get a comprehension about how rate affects these equilibriums too. So what we're going to do here is we're going to only look at bimolecular single step reaction, which is we're just going to use letters. So A plus B goes to C plus D. So we can write a rate expression for the forward reaction. So rate of the forward equals the rate constant A times B, and then we can do a rate expression for the backwards one. So we're going to do K dash equals C times D. Okay, so a Kc would just be the products divided by the reactants. Now we know at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So we can actually make those rate reactions equal each other. And if we tried to make it so that we had just the K's on one side of the equation, then I would have K divided by K dash, and then I'd divide C by A and B, and I'd be left with this expression here, which is really awesome. And we know that products divided by reactants equals Kc, so that means K divided by K dash equals Kc, which is so cool and so good to know. So we can actually compare the equilibrium constant of the forwards reaction with the equilibrium constants of the reverse reaction, and that ratio will tell us which way the reaction favours. And so if K is greater than K dash, then that means that Kc is large and the reaction proceeds and you have more products than reactants. And if K dash is greater than K, then Kc is small and the reaction barely proceeds and you've got more reactants. So isn't that awesome? So we can actually use all these principles we've learnt before, and we can now link rate into equilibrium constant as well, which is super cool. Yeah. So the final thing is we can actually then link Le Chatelier's principle into how it affects the rate constant. And so if we change the concentration of a system, this doesn't affect the rate constant at all, okay? And the reason why is because concentration doesn't affect rate, okay? So if it doesn't affect the rate constant, then the Kc stays exactly the same. Cool. Next one, what if we add a catalyst? Well, that means the rate constant of K and K dash, so the forwards and the reverse, are going to be affected equally. And so therefore Kc's not going to be affected. And what about temperature? Well, we know if you increase the temperature, it's going to increase the rate constant. And we know that by using Arrhenius's equation. And that's because the activation energy of the forward reaction and the activation energy of the reverse reaction are different. So like in an endothermic reaction, which looks like, like that, the activation energy here is massive in the forwards direction. So in the reverse direction, the activation energy would be tiny. And therefore the rate constants are going to be affected differently. And therefore the ratio of these will be different. And that's what causes Kc to change, which is so cool. So you're kind of finally getting as to why Kc changes when temperature changes and not with the other factors, which is really awesome. And so that's what I'm just basically describing down here with this endothermic reaction. The endothermic reactions have a massive activation energy in the forward direction and a smaller activation energy in the reverse direction. And so an increase in temperature will have a greater effect on K, as K is the forward reaction. And therefore, when Kc increases, when temperature increases, the Kc will also increase. And that's just because you're massively going to, if you've got this and you massively increase this one, this is going to go up as well. So that's pretty cool. So now you can kind of link in all of this. So kids kind of get stressed out about the Gibbs free energy stuff, and actually everything can be explained in this one kind of part here. So first of all, we know previously that a negative G means spontaneous, and now we can link that into that the forward reaction proceeds. So a negative G means mostly products. A positive G is non-spontaneous, which means mostly reactants, so the backwards reactions being favoured. And that a zero G, minimum energy, is equilibrium. Okay, now we can link that to Kc because we know that if you've got mainly products, your Kc will be greater than 1. Mainly reactants, your Kc will be less than 1. And both equal amounts, your Kc will be 1, which is really cool. We can calculate delta G by doing this equation. The only thing you've got to be really careful of is please make sure G and R have the same units, which is joules, not kilojoules. And the cool thing is that you can compare Kc. You can calculate Kc from your two rate constants, K being the rate constant of the forwards and K dash being the backwards. And so you can use that ratio to tell you where the reaction sits. So if K is greater than K dash, you get a large Kc, so more products than reactants. And if K dash is bigger than K, you'll have more reactants than products. And that is it, team. That is all the end of that part. And so here is your final bit of questions, 22 to 24. And yeah, that's it. Well done.